last time we talked about the substitution, okay, the substitution rule. And we did several examples of substitution rule. Okay, recall the idea of substitution rule. So the idea is we have the two operations, which is differentiation, i.e. taking derivative of functions. Here we also have integrations. And the fact is they are inverse operation to each other by the fundamental theorem of calculus. Okay, they are inverse operation. Now here we have chain rule, the chain rule. And then if we have one rule on the one side, and then we can get another rule by this, inverse operation. So which is called, which here correspond to the substitution rule. The substitution rule. Okay. Now last time we did this substitution rule for indefinite integral. Okay, substitution rule for indefinite integral. Let's see certain examples. Let's see this example. E to the power sine x squared times twice sine x cosine x dx. Okay, so this example. Now, once we have one example, an example, now the first question is check whether it is in the antiderivative. Okay, for this example, it's not in the antiderivative. Then we should use other techniques. So here we use substitution rule. Then the next question is what factors that we substitute? Okay, what factors that we substitute? Then in general, usually we don't have too many choice. Okay, so you can try to substitute its factor and see if it works. If it doesn't work, then choose another one. Once you have enough, examples, and then you will usually know what kind of substitution that we choose. Okay, for this example, you see, we let u be sine x squared. Sine x squared. Now, if we choose this u, now then we have du over dx. Du over dx, which will be, now take this derivative, sine x squared with respect to x. Then you see, this is the outer fraction is the power 2. So we use power rule, then we get twice sine x in the function can be fixed. And then multiply sine x derivative by chain rule. Okay, sine x derivative, then we get cosine x. So here we apply the chain rule. So we get a du will be du over dx times dx. Now du over dx we already know, so it's twice sine x cosine x dx. Okay, multiply dx. Then you see we have twice sine x cosine x. Okay, this, and also in this indefinite integral we also have this factor again. So this means we have the right choice. Okay, we have the right choice. So the original, indefinite integral will be use substitution. When we use substitution rule, we should substitute everything, including the differential. So the differential we substituted by du. Now this thing you see this e to the sine x squared. Sine x by our substitution is sine x squared, which is u. So this is sine e to the u du. Okay. Now this is e to the u du, which is in the antiderivative. Okay, which is in the antiderivative. So we can apply the antiderivative. So this is e to the u itself plus constant z. Okay. Then we return to original variable. So this we get e to the sine x squared plus constant c. Then we are done for this problem. Okay, then you are done for this problem. You can check backwards what difference it is. Okay, all right. More examples. Now, what you ask, what happens if we use substitution rule for definite rule? So substitution rule for definite rule, that is slightly different. It's slightly different. So we need to consider the upper limit and lower limit. Substitution rule for definite rule. Okay, substitution rule for definite rule, we need to substitute the upper limit and lower limit. Here is so a to b f gx g prime x dx. When we use substitution rule, so here, so for instance, when let u be gx, use this substitution, then you see g prime dx. We substitute the gx by u. We substitute the g prime dx by du. Okay, so here if we let this substitution, then du will be du over dx times dx. Now du over dx is u derivative with respect to x. U is g, so it's g prime dx. Okay, so this is the du. Okay, now the upper limit and lower limit we also need to change. So when x is a, x equals a, we let u, then we get u is gx, which is ga. Now when x is b, then we get u is g of b. Okay, so when we substitute the definite rule, when we use substitution rule for definite rule, then we need to substitute the upper limit and lower limit. Okay, so this is the difference. Then here this is ga to gb. Okay. Okay, prove. To see why this, we need to substitute definite rule. Substitute upper limit and lower limit. So suppose that capital F is an antiderivative. Antiderivative of little f. Little fx. Then we have this function, capital F at gx is derivative. By chain rule, the outer function is capital F, so this will be capital F derivative at g multiplied by inner derivative. So this outer derivative, so inner function fix dx, and they multiplied by inner derivative g prime. Okay, so chain rule, apply the chain rule. Now g prime is little f, so g prime is little f, so this is little f of gx times g prime of x. So we already find out antiderivative is of our integral. So we have this from a to b, g prime. So we already find out antiderivative, which is capital F at gx. Okay, so this is antiderivative. So by fundamental theorem of calculus, then we subtract the two endpoints. Okay, subtract the function value at the two endpoints. Okay, so we already find out antiderivative of the integral. So we applied here fundamental theorem of calculus. Okay, or Newton-Leibniz formula. So this is the capital plugging x by b, subtract plugging x by a. Okay, on the other hand, so ga, gb, fu du. Now capital F is an antiderivative of little f, so this is capital F at u evaluate at the GA and GB. Now this will be substitute U by GA, substitute U by GB. So this capital F at GB, subtract capital F at evaluate the U at GA. Okay, so you see the right side we have this is the capital F GB minus capital F GA, and then the last step we get a capital F GA GB minus capital F GB. So this they are the same. So you see, if we don't change the upper limit and lower limit, then we will have a trouble. Okay, then you see if we don't change upper limit of upper limit of this definite integral by GA and GB, then the result will be different. Okay, so to make sure the result is the same, we need to change upper limit and lower limit by the substitution that we use. Okay, by the substitution that we use. Okay, let's see some example. Let's see this example. 0 to 1, arctan x, 1 plus x squared dx. Now, first of all, you see this function arctan x over 1 plus x squared. Then you see, first of all, this is not in the antiderivative table. Okay, arctan x over 1 plus x squared. This is not in the antiderivative. Then we should use some other technique. And then let's see what do we know about arctan x. So we have arctan x. Now we know arctan x derivative. What is arctan derivative? Arctan derivative, check the derivative table. Okay, we did this using the idea of implicit differentiation. So we get this. Okay, so you see we have 1 plus x squared. Okay, 1 plus x squared, 1 over 1 plus x squared. So the substitution that we choose is this. Let U be arctan x. Okay, then we have du over dx, which is 1 over 1 plus x squared dx, the thing. So then we get du will be du over dx times dx. This will be du over dx, we already know. So it's 1 over 1 plus x squared multiply dx. So when x is 0, then corresponding to u is arctan of 0. Arctan of 0 is 0 because tan 0 is 0. When x is 1, u will be arctan of 1, which is 45 degree power 4. Then the original definite integral will be 0 to 1. You see arctan x over, you can write it as arctan times 1 plus 1 over x squared. Division we can write as multiplication. Okay, divide by 1 plus x squared. So we can write as multiply the reciprocal 1 over 1 plus x squared. Okay, don't forget the differential dx. Now you see we have the thing, this. Okay, they are the same. They are the same. So we can substitute 1 over 1 plus x squared dx by du. We substitute the tangent x by arctan of x by u. Okay, and then we substitute 0 corresponds to 0. We substitute 1 to power 4. Okay, substitute everything. Then you see u du. U du, this is in the antiderivative table. Okay, u du is in the antiderivative table, which is power rule. Okay, power rule. So u has antiderivative, use power rule. Then increase power by increase the exponent by 1. So power 1, then increase exponent by 1. So it's power 2. And then divide. So it's 1/2 u squared. So this is antiderivative of u. Okay. And then by fundamental theorem of calculus, we need to evaluate the thing at upper limit and lower limit, and then subtract. So this will be 1/2 pi over 4 squared minus 1/2 u is 0. Then we get this is the 1/2 pi squared over 16. So this is pi squared over 32. Then we are done for this problem. Okay. Another example. One to e integrated this function ln x over x dx. Okay. Now, first of all, this ln x over x, this function is not in the antiderivative. So we use other technique. So here we use substitution rule. Okay. Now, once we have this function, now the next question is, what substitutions that we choose? Now you see the integrand is a fraction, ln x over x. Then for a fraction, what we usually substitute is either denominator or numerator, or sometimes factors of denominator or numerator. So here, what do we substitute? Now, so we either substitute denominator x or numerator ln x. Now, which one actually do we choose? Now, first question is, if we substitute u by x, this actually does not change the problem. It does not change the problem. What we essentially do by substituting u by x, okay, is actually rename the variable. Rename the variable. That does not change this difficulty. Does not reduce this problem. So this is not looks like a good choice. It doesn't look like a good choice. Substitute the u by x. So we the remaining choice is ln x. Okay. So we let u be. So we try let u be ln x. And see how we substitute the differential. So substitute the differential. So we need to find du. Du will be du over dx times dx. So we want to change, substitute the differential. So du over dx is derivative. Okay, du over dx. U is ln x. Du over dx ln x derivative. ddx. Remember, ln x derivative. Ln x derivative is 1 over x. Okay, this is in the derivative of ln x. Multiply dx. Okay, so you see, we have x in the denominator. We have dx. Okay, so when x is 1, then corresponding u is ln of 1, which is 0. Ln 1 0. Okay, when x is e, corresponding to u is ln of e, which is 1, which is 1. Okay, so we have, this will be 1 to e ln x over x dx. So by substitution rule, this will be change upper limit and lower limit. 1 we change this lower limit corresponding to 0, upper limit correspond to 1. Okay, ln x correspond to u. Okay, then the remaining thing is 1 over x dx. So 1 over x dx, substitute the thing by du. Okay. So now we apply substitution rule, or now u du is in the under the table. Okay, so this will be 1/2 power u squared 0 to 1. So this will be 1/2 plugging 1, plugging 0. This is 1/2 minus 0. So this is 1/2. Okay. All right. Now, sometimes we have symmetry in the definite rule. Okay, symmetry plays a really important role, not just in mathematics, and also plays important role in physics. Okay, actually, the fact is, symmetry gives us, from symmetry we can deduce the fundamental rules in physics. Okay, the fundamental rules of physics. So it's really important. Sometimes if we have symmetry in definite integral, we can actually reduce the work. Okay, for instance, if we have all the function, let's see this example. If we have symmetries, so symmetry. If this definite integral has symmetry, so let's give it some definition. Remember some definition. A function is called a function f(x) is called an even function. If we know f negative x equals f(x), okay, for all x in the domain. Okay, some example. For instance, f(x) is x squared. This is even, okay, even function. You plug in negative x or plug in x. So for instance, negative x, plug in negative x squared, take squared, then you get x squared. The output is the same. Okay, for instance, x power 4, any even power, if you plug in negative x power 4, then you get the same thing as positive power 4. So any even power of x, we get even function. So for instance, cosine x. So you plug in cosine negative x, then the output is the same thing as cosine x. So cosine x is even. For instance, sine x squared is even, okay, because sine negative x squared, you get negative sine x squared, which is again negative 1 to the power 2. You get a sine x squared. Okay, so we have a lot of even functions. The fact is, for even functions, then we have the following. If f(x) is even, is an even function, then we have negative a to a f(x) dx equals twice 0 to a f(x) dx. Okay, the idea is even function is symmetric with respect to the y-axis. For instance, y equals x squared. So it's a parabola. Okay, y equals x squared. Y equals x squared. Now from a to a, negative a to positive a. Okay, this is 0. This is x. This is y. The idea is from negative a to a. We have by symmetry, we have two congruent region. Okay, so from negative a to a, so by symmetry we have twice. Okay, we have two regions. Okay, we have from 0 to a. By symmetry we have twice that thing. Okay, f(x) dx. Okay, so this is what this substitution says. Okay. Now, even function is symmetric with respect to the y-axis. Now, another thing is the order function. So, definition. A function f(x) is called odd if f negative x equals negative f(x). Okay, for example, for x. Okay, example of odd functions. Odd power, x cubed. X cubed is odd because if you plug in negative x, take the cube, then -1 to the power 3, you get -1. So this negative x cubed. Okay, so this is negative original value for in sine x. So if you plug in negative x, then you get a sine negative x. Now sine is odd, so you can factor. So you got a negative sine x. Okay, for instance, tangent x. This is again odd. Tangent negative x, then you get a negative tangent x. Okay, odd functions. Now fact, odd function is symmetric. Symmetric. I mean, it's graphs of all the functions are symmetric with respect to the origin. So for instance, what is sine x? Graph of sine x. Graph sine x looks like this thing. Okay, now here we have this piece. So if you have a point on the graph, then you have another point. So if you have a point here, you have another point with respect to the origin O. Okay, with respect to the origin O. With respect to the origin O. So it's symmetric with respect to the origin O. Okay, they are symmetric with respect to the origin O. Okay, symmetric with respect to the origin O. Now, for instance, what's the tangent x graph? Graph of x cubed. Y equals x cubed. Okay, x, y. So it's symmetric with respect to the origin O. Okay, any point, we have a corresponding point. Okay, they are symmetric with respect to the origin O. Okay, so this is the property of all the functions. Now, if we have all the functions, if fx is odd, is an odd function, then if we integrate negative a to a for any e fx dx, then we get immediately this is 0. This is 0. The idea is all the functions are symmetric. Okay, so here if this is negative a and this is positive a, okay, by symmetry, this part we get positive area, this part we get negative area, and then by symmetry they are symmetric. They have the same area, but one is positive, one is negative. So this is the idea. Okay, so they cancel out each other. Or we can also do it in another way. Okay, so we can also do it in this form. This standing rule we can break into pieces. Okay, by the gluing properties from negative a to 0. Plus from 0 to a, gluing property. Okay, gluing property. So this is gluing property. So we can cut it into two pieces. And then for the first one, for the first integral, so negative a to 0 from fx dx, we can use substitution. Let t be negative x. Okay, then this will be f negative t, x will be negative of t. So dx will be negative dt. This is negative dt. So when x is negative a, t is a. When x is 0, t is 0. Okay. Now, because here the function is odd, so we can factor the negative one out. So it's negative ft multiply negative dt from a to 0. So negative cancel negative. Here we have two negative. So this will be a to 0 ft dt. Now if we switch upper limit with lower limit, then we get then we get an actual negative one. Okay, so it's 0 to a. ft dt. Now, if you use original variable, this will be 0 to a fx dx. Okay, so this will be retain the original step. So this will be negative 0 to a fx dx plus 0 to a fx dx. Now, this thing plus negative of that thing, so they cancel out each other. So we get a 0. Okay, so this we get a 0. So by symmetry, this is easier. If we know a function is odd, then we can immediately write down the answer without evaluating this. Okay, for instance, some example. Okay, we can write down any examples. Let's see. Odd power. You see, for instance, x to the power 2021, for instance, sine times x squared. Okay, so for instance, fx be the thing. So even function times odd function is then we get odd function. Okay, even function times odd function, then we get odd function. So you see, if you check negative f negative x, then you get x negative x to the power 2021 times sine negative x squared. This will be negative x to the 2021. Now x squared is just x squared. Now this is, you see, this is negative fx. So this domain is defined everywhere. So this means, by definition, fx is an odd function. Odd function. Then, if we have an odd function, then for instance, let's do negative pi to pi, x to the power 2021 times sine x squared dx. Okay, now this example is very complicated. It's very difficult to, it's difficult, not easy to find its antiderivative directly, okay? Because it's complicated. However, by symmetry, we can reduce the work, okay? Here you see the upper limit and lower limit, they are symmetric, negative pi to pi. And then we can conclude according to the property by symmetry, okay? By symmetry, if we have all the function, then it's integration with respect to the symmetric interval. Okay, then we get this negative area times positive area, then we get 0. Okay, we don't need to find this antiderivative at all. We don't need to find this antiderivative at all. We can easily write down this is 0. Okay, so just by symmetry. Okay. Okay, let's see more examples of substitution in programs. Okay. Okay, example. Okay, this example, what do we substitute? First of all, this integrand is a fraction. Now, if we have a fraction, usually what we substitute is denominator, numerator, or a factor of them. Okay. Now here you see the denominator, the numerator is easier, is 1, so there's nothing to substitute. And then the numerator is, the denominator is x log x. So we need to consider to do something with denominator. Now what do we substitute? Now, a general rule is if we substitute, then we can simplify this problem. So this example, we actually substitute a factor of the denominator. Because if we choose let u be ln x, then you see du over dx. This will be dx, ddx, ln x derivative. Now ln x derivative already know is 1 over x. Then du will be du over dx times dx. Du over dx is 1 over x, okay? According to what we just did. Then we multiply dx. Multiply by dx. So this will be, now this will be, then we substitute x ln x dx. Now x, 1 over x dx. You see, if you write the thing as 1 over ln x times x, 1 over x dx, we can write it in this form. Then you see 1 over x dx, 1 over x dx, which is du, okay, du. So we substitute the thing by du. Now remember, u is ln x, u is ln x, u is ln x. So this is the u, okay. So this is the u du. U du we get, we can check antiderivative table. So this is the u squared. Increase power by one, increase the exponent by 1 and divided by power, then divided by 2 plus constant c. The last step, return to original variable. 1/2 u squared, u is, remember, ln x is squared plus constant c. Then we are done for this problem. Okay, then we are done for this problem. More example. Okay. Now this example, what do we do? First of all, we can, let's see, this problem, denominator is 1 plus x squared, numerator is 1 plus x. First of all, it's not in the antiderivative table, okay? Then what we do is we do the following. We write it as, we split terms. Okay, and then according to the linear property, we can write distribute. Linear property. Okay, so that we get a linear property. Then the first part, that's easy. Okay, it's in the antiderivative table, so it's arctime. Using antiderivative table. Now how do we do the second part? So for the second antiderivative, we do the following. Okay, we substitute let u be 1 plus x squared. Okay, then you see, if we use this substitution, what do we get for du? Du is du over dx times dx. Du over dx. One plus x squared, its derivative is 1 has the root 0. X squared has the root 2x. So this is 2x dx. Okay, so you see x dx. Solve for x dx. This is 1/2 du. Divide both sides by 2. Okay, divide both sides by 2. Then this will be substitute the numerator, substitute denominator. So if you write more clear, so it's the x dx. So this will be 1/2 du over u. Okay. Now this is the 1/2 u du over u. Okay. Now du over u is antiderivative is in the antiderivative table. So it's the 1/2 ln of u, also value plus c. So this is 1/2 last step return to original variable 1 plus x squared plus c. So this part we actually get this part is ln 1/2 1 plus x squared plus constant c. Then we're done for this problem. Okay. More example. Okay, now what do we do for this problem? What do we do for this problem? What substitution do we choose? What substitution do we choose? What substitution do we choose? Anyone know? Okay. This is a fraction. Okay, if we have a fraction, then what we do is we either substitute denominator, numerator, or factor of that thing. So here we substitute the more completed one, the denominator. So we let u be 1 plus x, 1 plus e to the x. Then what is du? Du over dx, then du over dx, take the derivative d dx, 1 plus e to the x. 1 has derivative 0, e to the x has derivative e to the x. So we got e to the x. So we get a du, which we got a du over dx times dx. Du over dx is e to the x multiplied e to the x. So if you write the original definite integral as this thing, e to the x multiply e to dx over 1 plus e to the x. Now you see e to the x dx, e to the x dx. We're substituting by du, by what we just did last step. Then 1 plus e to the x, by our substitution, this is the u, okay? So this du over u. Du over u has antiderivative is, it has antiderivative log of the value of u, okay? And then we retain the original variable x. U is 1 plus e to the x, which is positive, so we can take off the absolute value symbol. And then we are done for this problem, okay? Then we are done for this problem. Okay, what do we do for this problem? What do we do for this problem? Okay, first, this is not in the analytic table. Okay, so we should do something else. Next question, if we do substitution, what substitution factor do we actually choose? Okay, when we choose substitution factor, then the principle is we should get something that is in the antiderivative table. Okay, in the antiderivative table. Now you see, if you look at the power here, it's power 4. It's power 4. Now in the antiderivative table, we don't have power 4. We don't have power 4. However, we have this power 2. If you compare, it looks like this thing. It looks like this thing. Now this one we know is antiderivative, which is octane. Okay, so if you, so this is why you should remember every item in the antiderivative table. So this is octane x. Now if you compare, this is degree 4. And then what we know is degree 2, 1 over 1 plus x squared is square, okay? Now, how do we make degree 4 a power 4 into a power 2? What substitutions that we can use such that we can make this power 2 into power 4? Or power 4 into power 2? Well, we just let u be x squared. Then u squared will be x squared squared, which will be x power 4. Okay, so that we let u be x squared, then we get a power 4. Okay. Then you see du. What is du? Du is du over dx times dx. Du over dx is u's derivative, ddx over dx. Now remember, x squared derivative is 2x. So it's 2x times dx. Okay. Now 2x dx, so this implies x dx. Divided both sides by 2, so it's 1/2 d of u. Now the original indefinite integral x dx over 1 plus x squared. Then we can substitute the x dx by 1/2 d of u. And then we can substitute the 1 plus x squared, x power 4, then this is the 1 plus u squared, okay? Remember, u is x squared. U squared will be x power 4. And then factor out this 1/2 u over 1 plus u squared. Now this is in the antiderivative table, okay? In the antiderivative table. So we just, it's the 1/2 arctine of u, okay, plus constant c. And then the last step, substitute u by x squared, return to original variable, arctine, x squared plus constant c. Then we're done for this problem, okay? More examples. More example. Okay, let's see this example. Okay, the integral is x over square root of 1 plus x squared. Now, first question, this is not the integral is not in the antiderivative table. So we should use what we learned today, substitution. Okay, substitution. Now, the next question is, what substitution factor that we actually choose? Now, if you observe the integral is a fraction. Now, once we have a fraction, usually the natural choice will be denominator, numerator, or factors of them. Okay, so if you see the numerator is x, is very simple. So if we substitute u by x, it does not simplify this problem. So we will try to substitute the more complicated factor. In this situation is we let u be, you can use this, the substitution factor is not unique. You can actually try to substitute x squared, square root of the thing, or you substitute the u by x squared plus 1. They both work. Now suppose we let u be the thing. Then we get u squared, which will be square root of x squared plus 1 squared. Squared cancels square root, so this will be x squared plus 1. Then we differentiate both sides. Both sides. So you can actually get this d u squared equal to d x squared. This side you get a 2u du. This side you get a 2x dx. Of course, you can differentiate with respect to some variable. Differentiate with respect to some variable. However, by chain rule, you can just differentiate both sides. The left side with respect to u, okay? You can view u as a variable. The right side you view x as a variable, and then you are still get the equals thing. This is because here by chain rule, this is we applied it essentially chain rule, okay? So this is actually more natural to write differential rather than derivative. The thing is, differential is well defined. Whatever variable you use, okay, is well defined. Now, if you use, you choose a specific variable, then if you take derivative, it is not the same thing. Okay, we need to consider chain rule. Okay, if you change the variable, then you get actually a different derivative. So here, this is more natural to write as differential form. So it's differential form. Okay, you can check this by differentiate. So for instance, u squared over dx, which will be d dx, u squared x squared plus 1. So this you get a 2x. So you get the right side by chain rule, so 2u du. 2u, so this by chain rule you get a 2u times other derivative, u squared derivative is 2u. And then multiply in the derivative du over dx, which you get a 2x, the right side. Then multiply both sides by dx, then you get a 2u du, which is 2x dx. So you get the same thing. So essentially we apply chain rule. So you see we get the same thing. Essentially we apply chain rule. So it's more natural to write as differential rather than derivative. Okay, so you see we can write it in as, so you get cancel the factor 2. So you get a u du will be x dx. So the original definite integral will be the thing. Now, if you remember the dx, the relation of dx and the integral is multiplication. It's multiplication. So this is x multiplied dx over square root of x squared plus 1. Then we can apply substitution rule. Substitution. Now x dx, we already know by the last step, x dx is u du. Now according to our substitution, the square root of our substitution is u by square root of x squared plus 1. And this is the denominator, which is the u. And then this is, u cancel u. So this is 1. 1 times du is just du. Okay. Now remember, this integral and d cancels each other. Up to constant c. Up to a constant. So they cancel each other. So the remaining thing is u plus c. Remember u, what is u? By our substitution, u is square root of x squared plus 1. Once we're done, we plus c. Okay. Then we get this is x dx. This is the square root x squared plus 1 plus c. You can check, differentiate the thing. You can differentiate this the right side and check you get the integral. Okay. Okay. Example. Let's see definite integral 0 to 2 x minus 1 dx to the x minus 1 to the power 25. Okay, so now the integral is a polynomial x minus 1 to the power 25. So we don't want to expand this 25 degree, otherwise it's a disaster, ugly algebra. So what we do is we try to use substitution. So we let u be x minus 1. Then du over dx is dx x minus 1, which is x minus 1 derivative is 1. So actually we know du will be du over dx times dx. So du over dx is 1 times dx. So du and dx, they are identical. They are identical. So then by substitution rule, by the substitution rule, then we have 0 to 2, x minus 1 to the 25 dx. Now substitute this, x equal to 0, then we get t equal to x minus 1, which is negative 1. X is 2, t is x minus 1, then we get 1. So it's a negative 1 to 1, t to the 25 degree. Now dx is dt, dx is dt. So according to power rule, 25 degree, then we get 26 degree, and then divide 1 over 20, multiply 1 over 26. From negative 1 to 1, fundamental theorem of calculus. Fundamental theorem calculus. Okay, subtract the two function values at the two upper limit and lower limit. So plugging in 1 and plugging negative 1. Then we got this is the 1 over 26 minus 1 over 26, which is 0. Okay, or we can easily, you see, x t to 25 degrees is odd, and then this interval is odd. So this actually, you can straightforwardly conclude this is 0 by symmetry. By symmetry. Of course, you can conclude directly by symmetry. Okay. More examples. Zero to y half arc sine x over square root 1 minus x squared dx. What do we get? Okay, arc sine x over square root 1 plus x 1 minus x squared. So it's a fraction not in the entity table. Then we should consider substitution. Then what factor that we substitute? Now if you see arc sine, remember once you see arc sine, you should immediately realize arc sine derivative, which is y over square root 1 minus x squared. So what we substitute is arc sine. Okay, that u will be arc sine. Then this du over dx is arc sine derivative, 1 over the thing. So then if x is 0, u is arc sine of 0, which is 0, because sine 0 is 0. When x is the y half, what is u? What is arc sine y half? What is arc sine y half? What is arc sine y half? It's very easy, arc sine y half. Arc sine y half is pi over 6. Okay, pi over 6. So this will be, okay, this will be according to substitution rule. So 0 to 1 half, if you write the thing as arc sine x times 1 over square root of 1 minus x squared dx. Then, so with this we can get du over d. Du is actually multiply both sides by dx. Okay, this is exactly du. Exactly du. Okay, so this is du. This is u is 0 to pi over 6. So this will be 1/2 u squared 0 to pi over 6. So this will be 1/2 0 to pi over 6 squared minus 1/2 0 squared. So you can easily compute this. So this is pi squared over 72. You're done. Okay. More examples. More examples. Zero to pi over 3 sine theta cosine theta squared d theta. Okay. Okay, what's this thing? Okay, so the integral sine theta over cosine squared, you can write it as sine theta over cosine theta times 1 over cosine theta. So sine over cosine, then we get tangent. 1 over cosine, then we get secant. So this is essentially 0 to pi over 3 tangent theta times secant theta d theta. Remember, we have antiderivative table. Tangent secant, this is in the antiderivative table. It says, what's the antiderivative? Tangent secant, what's the antiderivative? Its antiderivative is secant theta, okay? Its antiderivative is secant theta from 0, and then according to fundamental theorem of calculus. Fundamental theorem of calculus. So it's antiderivative secant theta. Then we evaluate these two endpoints and then subtract. So the secant of pi over 3 minus secant of 0. Now remember, secant theta is 1 over cosine. Now cosine pi over 3 is 1/2. Okay, so this is 2 minus cosine 0 is 1. So cosine secant 0 is 1 over 1. So it's 1. So 2 minus 1, so this is 1. Okay, more examples. Let's see this example. Okay, so the integral is a trig function, okay? Sine cube of x could multiply cosine x, okay? So what substitution do we choose? What substitution do we choose? Now, in general, if we have powers of sine and cosine, the general thing that we substitute is either sine x or cosine x, okay? In this case, we either substitute sine x or cosine x, okay? Now, if we substitute, let's see if let u be sine x, u be sine x, then what is du? Du over dx will be sine derivative, dx. Sine x derivative, we get cosine x. So du will be du over dx times dx. So we deal over the x with cosine x dx. And you see here we indeed have cosine x dx. So this will be by substitution rule, sine x cubed cosine x dx. So substitute cosine x dx by du, okay, by du. So then sine x cubed, this will be u cubed. Now this is sine u cubed du, now which is in the antiderivative table by power rule. So this increase the power, increase exponent by 1, and then divide the exponent. So we get a 1/4 u to the power 4. This is a quarter, retain the original variable, sine x to the power 4. Okay. Now, what if we substitute the cosine x? Okay, so if we substitute u be cosine x, then du over dx will be d dx cosine x. Cosine x derivative is negative sine x. Okay, negative sine x. Negative sine x. Then you see what we learned. What we did is sine x derivative, cosine x derivative, negative sine x. So the original thing is sine x cubed cosine x dx. Okay, cosine x dx. Cosine x is our u. Okay, so this actually we get du will be negative sine x dx. So we have factored negative sine x dx. So what we do is this: we split the factor sine x squared times sine x cosine x dx. Split the factor of sine, then we switch sine x squared cosine x sine x dx. You see, we indeed have a factor of sine x dx. Okay, sine x dx. Then we can use trig identity, sine squared plus cosine squared is 1. Okay, so we get a sine squared is 1 minus cosine squared, which is 1 minus u squared. Remember, our substitution is u be cosine theta, cosine x. So this is 1 minus u squared. Now cosine theta, cosine x is u. Now sine x dx by our substitution is negative du, negative u. Okay. So this will be, if you multiply negative 1, then this will get a multiplied negative 1. So you get u squared minus 1 times u du. So this you get u cubed minus u du. And then apply power rule. So you get a polynomial in u, and then apply power rule. So it's a quarter power 4 minus 1/2 u squared plus constant c. And then retain the original variable. Okay, so although you see we use different substitution, we still they both work in this example. For this example, they both work. Now, although we get different answer at the first side, 1/4 sine x to the power 4, and this result, they look different at the first side. Actually, they are different. They are the same after a constant. Remember, we have a lot of trig identities. If you apply trig identity, you will realize this is actually the same function up to a constant. Okay. Remember, antiderivative is only determined up to constant. Okay. So it's okay if we get different answer up to a constant. They looks different, but they are the same up to constant. Okay. More examples. Okay, now this is not in the entry table. This is not in the entry table. What we plan to do is we try to use substitution rule. Now you see here, remember for secant and tangent, so we have derivative of tangent. Remember derivative tangent, what do we get? Is secant squared. Okay, derivative tangent, we get secant squared. Okay, then you see what we substitute is, let u be tangent theta. Then du over d theta will be tangent theta derivative, we get a secant squared. So we get the du will be du over d theta times d theta. Du over d theta is secant squared. So multiply with d theta. So we get du secant squared d theta. So you see we have secant squared d theta, secant squared d theta. They correspond to each other. So this means our substitution is right. So then use our substitution. Tangent squared theta, and then secant squared theta d theta. And then this we substitute by according to what we get, which is du. Okay, du. And then u is tangent theta. U is tangent theta, remember? So we substitute tangent theta by u. So the u squared du. And then we apply power rule. U squared du, apply power rule. So the u cube divided by 3 plus constant c. Then finally we return to original variable. Return to x. So the 1/3 tangent theta is the original variable is theta. Tangent theta cube plus constant c. Then we are done for this problem. Now here, the trig function, they actually form one specific category we actually try to deal with. We have two lectures on one lecture on Wednesday, one lecture on Friday. We will continue to talk about this trig identities and trig integrals. Specifically, they have their own technique to deal with. Okay, this will be the last section of this semester of the trig identity and the trig integrals. Okay, now we have 2 minutes. Maybe let me just stop here.